Okay, morning everyone. How are you? Good. Ready for some more GIS? Yeah, cool. Okay, just a quick announcement about the field trip. I did send a message yesterday, just an announcement to say where to be, when, and what to do beforehand. So if there's any questions about that, let me know. Any questions about it? Now? You can always come and ask me later, but no. I know it's an early start, but it gets hot if we... Yeah. Yeah. If anyone desperately wants to go there themselves, then I don't encourage it, because if everyone did that, it would be a nightmare to organize. So I prefer people to go on the bus. But if for some reason you really want to drive yourself there or something, then email me, and I will send you instructions. Yeah, because you'll have to meet. You have to meet the bus probably outside the property, and then we'll go in. So anyway, but so if anyone really wants to, I don't want people to do it really, because it's a bit of organising. But yeah, if people do want to, then just email me. Yep. Okay. I did. So if people have mobile phones, I did suggest you download the ArcGIS Explorer app. So we're going to do some surveys out there, and I've made some data available online for where those survey sites are. I'll explain to you what you're going to do with it when we get there. But if you're able to do that and find that data set, then yeah, please do so. If you have any difficulties with that, just let me know. Okay? Yeah. Right. Right, we're gonna do a quiz. I've tried to get more of these. Our school doesn't have any more. The box that I got used to have like 100 or something in it. We've got about, they tell me they got 48 because I keep losing them. So I know there's a few people without them. I know the library have some, so I'm going to, later on today, I'll see if I can get some from the library. Someone gave me one that had a flat battery. That was you, wasn't it? Yeah. When we go over, I haven't got the battery yet. I'll have to go to the tech people in our school and get them to replace the batteries, but I'll do that when we're over in the labs. Yeah, so if anyone has a battery that's flat as well, let me know, and I'll go and get the battery replaced. Yep. I just didn't get a chance yesterday. Yep. And hopefully, in the next couple of days at least, So if you don't have one, I guess answer it in your head, and if you're, as long as we have enough people answering, I think we can have a discussion. Yeah. So. Okay. So. We're going to run the slideshow, and we'll see. So yeah, if you've got your clicker, if you haven't got one, maybe share it with someone, answer it in your head. We'll just make do for now. But okay. So this is just a revision on yesterday. Yep. Okay. All right. So this is a a question about projections. So we talked about projections. You did an exercise yesterday in the prac. So suppose you need to choose a projection to calculate the direction from one village to another. Which one of the following projections would be the best one to use? An azimuthal projection, an equal area projection, a cylindrical equal area projection, or a plate carré projection? Okay, I'm getting some responses. And if you forgot to bring your clicker, try and remember tomorrow. So some people forgot because we're getting fewer responses today. Or some people are not here. Okay. I've got about, yeah. Okay, well, let's see what people said. Yeah. Yeah, so most of you got that right. So it's an azimuthal projection. So an azimuthal projection actually preserves shapes and directions from the center. So if your projection is centered on where you want to calculate the direction from, direction from, then you can use the azimuthal projection. These two are equal area projections. You'd use them if the purpose of your map is to calculate areas, because it preserves area. It'll distort other things, so it'll probably distort. These would probably distort directions. Okay. Yeah. So remember, usually projections are designed to try and preserve one aspect of geometry, but at the cost of that, they distort other things. Yeah. So it's yeah. Okay. Make sense? Okay, so which one of the following would be best represented by a continuous field? Atmospheric pressure, roads, buildings, vegetation communities. Okay. Yeah. So that's right. The obvious one is atmospheric pressure, which most of you answered. Actually, I think, in some cases, vegetation communities could be right too, because it depends how we represent vegetation communities. If we represented them as categories, then probably we wouldn't represent that as a continuous field. But we could represent them as something like some continuous measure of community structure, like number of species, for instance. So it could, you know, or I don't know, some structural measure of vegetation, like canopy height. So in that case, we could potentially represent vegetation communities as a continuous field as well. So, but the obvious one is atmospheric pressure. So which one of the following is not a characteristic of discrete objects? They have well-defined boundaries, they can be counted, they can be described by points, lines, or polygons, and they must fully cover space. So they don't need to fully cover space. So if you think about a vector layer, you've been working with shape files over the last couple of days, you can actually have holes in those. You can have places where there's no objects. So they don't have to fully cover space. They can overlap as well, actually. So your polygons, for instance, can overlap. So there's no reason why you can't have multiple polygons that overlap in the same data layer. Okay, so yeah, what you can't have are different types of vector data models in the same layer. Okay, so you can't have points and lines in the same data layer. Okay. So the universal transverse Mercator, or UTM projection, is largely conformal and equal area within zones, but not across zones. Is this statement true or false? Yeah, it's true. So most of you got that right as well. So it's you remember the UTM projection has 56 zones, a north and south. Oh, sorry, yeah, 60 zones. Sorry, we're in zone 56 here. And as long as you're within one of those zones, so that if you remember the map, there's sort of these long, skinny zones running north to south. And as long as you're within one of those zones, it's a very useful projection because it does preserve shapes and directions and also areas, so and distances. So it's a useful projection for using in generally for smaller areas. So as long as you're within a zone. So if you're doing sort of regional analyses at the scale of something like Southeast Queensland, it's a very useful projection. Okay, and there's yeah.
Recalling from the lecture yesterday, the zones across, so for that question about Queensland,
Yeah.
it seemed that Queensland, I think, was covering 3 of those zones.
Yeah.
How does that work then?
Yeah, so if you're working at the scale of Queensland, you wouldn't use this projection because it goes across. I think Southeast Queensland is within zone, one zone possibly, but I'm not sure. It might go over into another zone in the western part. But yeah, so if you're working at the scale of the whole of Queensland, then yeah, this wouldn't be an appropriate projection.
What would you use for Queensland?
It depends what you're doing. So if you're interested in areas, I often use Alber's equal area projection. It works quite well. For directions and distances, I'm not sure. You'd use an equidistant projection. Yeah, so it depends what you're doing. And actually, you might use, if you're doing a single analysis and your one part of the analysis is about calculating areas, one part is about calculating distances, you'd actually use 2 different projections to do those different things. And that's quite common to do. So you have to think carefully about what projections you use for what parts of your analyses. Yep. Yep. There's the UTM projection. There's a Geographic Datum of Australia version of UTM, which I think you used yesterday in your prac. So that's the GDA 1994 projection. It's slightly different from the UTM, but it's essentially the same. But it's a sort of national grid version of that. If you use the UTM or the GDA, it doesn't really matter. They're more or less the same. They're out by a few centimeters or something difference, but not very much. Okay. So the exact shape of the Earth, which is an ellipsoid, is important for calculating geodetic latitude because A, the shape of the Earth must be known to project it onto a flat surface. The shape of the Earth influences the angle that a line drawn perpendicular to the Earth's surface makes with the equator. That's a mouthful. The volume of the Earth depends on its shape. Or D, the Earth changes shape over time. So which one of those is most true? Why do we need to know the shape of the Earth? Okay. Yeah, so most of you got that right. So it's B. It's a flattened sphere, basically. So as you move across north-south along that sphere, then remember the geodetic latitude takes a perpendicular line from the surface of the Earth down to the equator. So as you move across that, going north or south, the shape of that Earth matters. It influences that angle. Whereas if it was a perfect sphere, it wouldn't. Yep. Well, yeah. Okay? Easy? All clear? Okay. Any other questions from yesterday before we move on? Okay. So you're all experts on projections now. Good. So yeah, I mean, getting those ideas of projections clear in your head is really important because you can get your analyses quite wrong if you don't think carefully about it, as you saw yesterday in the prac. Okay. I'll just mention quickly before we start about the prac today. If we can find it. So today we have a little question at the end. So this is part of your assignment. So generally, and you can find on Blackboard the descriptions of the prac assessments. which I have a description of on Blackboard. So basically, for the next two practicals, there'll be a question at the end, and today's question is really just, so today you're going to do we're going to talk about how we get data into a GIS and capturing data. So you're going to do an exercise in digitizing and importing data into a GIS. And then there's a question at the end. So this question is really, you're going to do some digitizing of sand mines in Stradbroke Island for a hypothetical exercise that you might do restoration of those sand mines, and you're trying to map them out to identify where you might do restoration. And so the question here is really about, once you've done that, thinking about the accuracy of your mapping and how you might measure that accuracy. So we're going to talk about accuracy and measures of accuracy as well today a little bit. So these questions largely are just getting to think more critically about what you've done. And if you read the description of the assignment, I want you to write a maximum of 200 words for this, so no more. So they're short answers, so they're a paragraph basically at the most. And so what I would do, I'd read that first before you start your practical, so you know what you need to do at the end. And what I want you to do, I'll put a link up for a Turnitin submission, so when it's due, today and tomorrow's questions associated with the practical, you can submit through Turnitin on Monday. Okay, it's due by 4 p.m. on Monday. Okay, so you should be able to do this probably in the prac. Maybe you need a bit more time, but they shouldn't. Yeah, the idea is not. They shouldn't take too long to do. Okay, is that clear? Yep. For today, there's one question. Yep, and then tomorrow there's another question. So they're up on Blackboard now. So if you wanted to look ahead and see what you need to do for tomorrow. Tomorrow is mapping, and basically, I can talk about that tomorrow, but there's another question around mapping and communication of maps and so on. Yep. So generally, they are about, just thinking critically about what you've done. You can see on the description of the assessment, you can see the marking criteria. So marking criteria, so there is a component for sort of application or description of GIS technology. In some of the questions, we ask you to do some of the application or at least show some of the application or describe aspects of GIS technology. There's a component of critical thinking and then presentation. Okay, so also look at your marking criteria because we'll mark to that criteria. Okay, but it's really about demonstrating that you understand the concepts, you've been able to apply them in the lab, and also thinking critically about what you've done. I think it's an important part of GIS is not just pressing the buttons and doing the analysis, but understanding what does it mean. Once you've done it, how do we interpret it, and what does it mean? What are the likely limitations? And that's a really critical skill to develop. So there's a real focus on that. Okay? And if there's any questions, grab me in the pracs, and I can explain anything that's not clear. Okay. All right. Okay, so today we're going to talk about what are called data capture. So data capture is really how do we get GIS data into a GIS. So we've talked about the conceptualization of going from the real world to data models. We talked about how two main types of data model that we use in a GIS. So today's really about where do we get that data from? What are the sources of that data? What does that data look like? And so on. So we're going to talk about what data capture is, and talk about split it into two types of categories: primary data capture and secondary data capture. If you read the book, the chapter in the book, the Jensen and Jensen book, it talks about in situ and ex situ data capture, so a different conceptualization of different types of data capture, and I'll sort of try and refer to that as well. So that's what we're going to do. So really data capture is really, if we define what data capture is, it's the collection of information from the real world, and then the data capture bit is actually transferring that into a format that a GIS can read. So, and these data sources can come from a wide range of sources. They can be maps, just hard maps, paper maps. They can be satellite imagery. They can be digital data collected. They can be even data that's that's on paper copies of data, tabular data, or ideas that people express. So you can have georeference ideas about how people feel about green space and those types of things. So these data sources come from wide range of sources, and the data capture process is how you sort of take that and get that into a GIS. When you do that, once you've done that, there's a whole load of processes that really is about data editing and formatting and correcting that data and improving that data that I'll documenting that data that I'll briefly talk about as well. So that's sort of the what data capture is. You've seen this slide before. This is something I showed yesterday. In terms of the types of data we might want to collect, and there's two main components. One is the spatial attributes, so we need to know where things are, and but we also need to know non-spatial attributes. So there's data associated with spatial locations that we get from different sources, or potentially from different sources. So I will talk about both. I mean, there's how do we capture those spatial attributes and also those non-spatial attributes. Okay. So I told you about, I guess I mentioned that these two different types of primary and secondary data capture. But what are they? Do people know what they are? What's the distinction between the two? There's some examples there. Sorry. Yeah, sort of. Yeah. So you're sort of saying primary is you do it yourself, and secondary is done for you or done already. Yeah, sort of. Not quite, but close. Yeah. Yep.
Primary is gathering information from the field. Secondary is gathering it from other sources describing the field.
Yeah. Yep. So that's sort of that's pretty close. So you're saying it's primary is collected directly from the field. Secondary is from some secondary source. Yeah. So that both are pretty close descriptions. I guess I would say that. I guess perhaps a clearer definition is that primary is collected directly in digital form, whereas secondary is usually something where we have it in non-digital form, collected. It's already been collected from the field, and then we're trying to get that into a digital form. So some examples in raster and vector. So primary data capture. Digital remote sensing images that are captured directly in digital form is an example of primary data capture. GPS is primary data capture as well. We're getting location information and using that to import that into a GIS. Whereas secondary data capture is taking maps and scanning them, for instance. So it's already been collected and represented in a map. Topographic surveys, if we place names and so on that are from atlases that we might digitize. So they're secondary data capture. I guess I would make the point that actually we don't do much secondary data capture anymore. Sorry. Yep.
So if you get GPS off Google Maps or something like that,
Right.
actually taking GPS measurements,
Yep.
does that count as primary or secondary?
Yeah, so in that case, you're thinking you go to Google Maps and you just identify a location. Yeah. That's different. That's not quite data capture because the data's already been captured by Google, whoever captured that data. So it's already in the GIS, and you're just extracting that information from the database. So what we're talking about here is actually going into the field and collecting that information to make that in a digital form. So in that case, you're just using Google Maps. You might say, well, I want to know the latitude and longitude of this location.
You're capturing that information for your purposes.
Yeah, that's right.
From a different GIS.
Yeah.
Okay, so it's more of a translation.
Maybe you call it a translation. It's actually extraction of that data that's already captured for the use of a particular purpose. So I think it's slightly different, but yeah. But if you, so what we're really talking about here is taking data and making it into a database essentially that allows you to then start analyzing and extracting data and so on. But we do. I was just going to say we don't do much of this anymore because I think early when GIS was first being developed, there was lots of this happening because we had lots of paper maps, we had data that was non-digital, and there was lots of effort in turning this stuff, paper maps and topological, topographic maps and so on, surveys into digital form. But we don't really do a lot of this anymore because almost all the current data capture is primary data capture. So we have, it's remote sensing, or it's collected in the field directly into a GIS. So I'm not going to talk too much about secondary data capture. Types of data capture too. So the Jensen and Jensen books try to split it into in situ and remotely sensed capture. So in situ really is collecting data directly in the field. So you're actually you're in situ at the site or the field site where you're located. So tracking giraffe with GPS would be an in situ data capture because the device that's collecting the information is actually in the field. Remotely sensed data or ex situ data capture is really when we're talking about things like satellite imageries, aerial photographs, where the detection device that's recording the information is actually remote from the actual location. Okay, so is that clear? That distinction? So yeah. So primary data capture, as I said, involves direct measurement of spatial information. It can be both raster and vector data. I'm going to talk about two main things: satellite imagery and surveying and GPS. And it's usually, well, I'd say usually here, it should always be direct transfer of digital data into your GIS. And as I said, almost all data capture these days is primary data capture. Okay. So I guess there's two main ways of collecting primary data capture, and one is ground surveying. It's based on measuring angles and distances from known points. These is a theodolite, and it's one way of collecting information. So you're going from known points to other points and working out locations that way. Or one that you'll be all aware of, and probably most of you have on your phones, is the Global Positioning System, or GPS. And these are based on signals from satellites of known position, that then you can work out your location. So this is really about getting spatial attributes. So I'm going to show you a quick video of an example of using GPS collars as a primary data capture example. If I can get it going, just bear with me. So I thought this is a sort of interesting example of where they've been using GPS collars to track cattle movement, and using that they're interested in whether having water available for cattle stops them going into riparian zones and damaging creek lines and so on. So I'm going to play this. It's just 4 or 5 minutes.
The sun shines bright.
So the project involves monitoring cattle activity in riparian areas, and a riparian area is the land adjacent to a stream bank or a watercourse. And they're really quite important for the ecosystem because they harbour a lot of biodiversity, and they're also important for soil condition because they stop erosion and they help filter the water that goes into the river itself. So the aim of the project is to see how much and how frequently and how long the cattle use the areas, because it's thought that cattle use in that areas results in sediments depositing into the water, and then that ends up in the Great Barrier Reef catchment. So it's actually quite difficult to quantify how much sediment is going into the water. So we're using GPS collars to see just how much they use the area, and if we can change the way that they use it to decrease the use in that area.
I feel the light, and everything is in its place.
We usually fit around 6 collars, so to 6 cows within a herd, just so that we can get an idea of where the whole group is moving about. We've got 25 collars here that we use on a couple of different properties, so we space them out to try and get as much data as we can and still get a representation of what the overall herds are doing. So we're using what's called high sample rate GPS. It operates at 1 hertz, which is, it gets a location estimate once every second. So it's quite a lot of data coming back through, but previous studies have shown that the more data and the more frequently it comes in, the more accurate the actual position is.
The sun shines bright as it moves across my face. I feel the light
That's cows.
and everything is in its place. Oh, I woke up feeling great. Today was made for me. And life is good the way it should, the way it was meant to be. And it's a beautiful day. Are ringing, children playing in the park while birds are singing. I am walking, and I am. The sun shines bright as it moves across my face. I feel the light and everything is in its place. Oh, I woke up feeling great. Today was made for me. And life is good the way it should, the way it was meant to be. And it's a beautiful day. It's a beautiful day. It's a beautiful day. Are ringing, children playing in the park while birds are singing. I am walking.
So far it's shown that by supplying a trough it does restrict their activity in the riparian area, but not completely. They still seem to go there, mostly during the hottest parts of the day, which we think is just purely for shade and they're getting away from the heat, but unless we do further studies we can't really tell what's going on, because the GPS gives us just an estimate of their location, not the actual behaviour of what they're doing, but it still gives us quite a lot of information on how they're using the paddock.
It's a beautiful day.
Okay. What I noticed from that was that cows don't seem to sleep very long, do they? They seem to stop for about 2 hours and then they keep going. Interesting. So that's just an example of primary data capture with the GPS, and I think the nice thing about that is it shows the spatial component and a temporal component. So you got space and time in terms of that geographic representation, and answering an interesting question. Okay. So quickly, we're going to look at how GPS works in a moment, and surveying, briefly, is basically, I guess, before GPS, and in fact, these days surveying uses GPS anyway, but typically would have in the old days would have a theodolite, and you'd have a known location, and then you would measure, you'd have a post, and you would measure distances from the theodolite to the post and the angles, and if you know where you are, where the theodolite is, and you know where and you know how far away you are on the angle to the post, then you know where the post is as well. So it allows you to work out, locations, exact locations. And you see people doing that on roads and so on. These days, we have these things called total stations. These are GPS enabled. And they have a antenna, this GPS enabled rod, and then it will measure distances from here to this reflector, and this will have a GPS on, and it'll automatically calculate the location of the rod. So it does all the work for you essentially. Downloads it directly into your GIS database. If you're under canopy, for instance, and you don't have, if you're under a canopy, you might not have access to enough satellites or any satellites. So if this is GPS enabled, you can actually still work out where that rod is. Okay. They often use these things called continuously operating reference stations. And around Australia, there's a range of those. And what they do, if you want to get very accurate, down to a few centimeters accuracy, just a straight GPS location probably won't be accurate enough. GPS location is probably accurate within maybe 5 to 10 meters. So these continuously operating reference stations actually correct so they're at known locations on the Earth's surface, and Australia has a network of these. If you want to read about them, they're here. There's a link there, and as long as you're within a certain distance of those, it'll correct your location to get a very accurate reading. Okay. So that's ground surveying. The one perhaps you use more often, the nod is GPS. So this uses an idea called trilateration, and it requires 4 satellites to get an accurate location. So basically, I'm going to play this video in a minute, which sort of explains better than I can, with a bit of maths on how a GPS works. But there's, I think, 20-something satellites in orbit. And basically, you're on the Earth's surface here. And the way trilateration works is that these satellites send signals down to your receiver, which might be your phone or your GPS. And because of the time it takes for that signal to reach from the satellite to you, you can work out how far away that satellite is from you. So then you can think about drawing these spheres around, so you can know. So if you've got one satellite, you know somewhere, and you know the distance to the satellite, you know you're on the surface of a sphere at that distance drawn around that satellite. But if you have multiple satellites, you can actually narrow that down. So if you have multiple satellites, you can narrow it down so that where they intersect is the location that you are. So you have these satellites, and then the intersection with the Earth's surface is the location. So that's what trilateration is. If essentially you can sort of get a rough estimate of your location using 3 satellites, but requires a 4th satellite, because the 4th satellite basically the video will tell you in a minute. It'll explain this a little bit in a minute. But has very accurate atomic clocks on these satellites, and basically the 4th satellite corrects the time of your GPS device, which isn't very accurate, to make sure that it's synchronized with the time of the satellite's atomic clocks. Okay, but I'm going to play you a video, and it explains it better than I can. But that's the general idea. Hang on. Yeah. I'll just cut and paste it. So there's a bit of warning, there's a little bit of maths in this, but hopefully it'll give you an idea. Once we pass the ad.
At over 20,000 kilometres above sea level is a constellation of satellites, each orbiting Earth every 11 hours and 58 minutes. These satellites are continuously beaming data down to us on Earth, which is in turn received by devices such as your phone or navigational units in your cars, allowing you to see where you are on the planet. There are a lot of misconceptions about how GPSs actually work, an example being that your phone and the GPS satellites are both talking to each other. So let's get down to it. How do GPSs work? GPS stands for Global Positioning System, which works through trilateration, not triangulation or multilateration, which is commonly misconceived. There are many different types of navigational satellite systems from countries across the world, but the most popular and commonly used system is Navstar, which is the USA system. There are, however, Russian, Indian, Chinese and European equivalent systems, although the Indian and Chinese systems sit in a geosynchronous orbit above their countries, which means they are not worldwide systems. The Navstar system, which is simply referred to as GPS, is what we will be focusing more on, although most phones and devices tend to have the capabilities to use both GPS and GLONASS. GPS satellites are set up in such a way that from almost anywhere on the surface of Earth you should have a direct line of sight of at least 4 GPS satellites. This is quite important on the basis that GPS point positioning requires at least 4 satellites to calculate 3 position coordinates and the clock deviation. As GPS units are receivers, there needs to be something sending some sort of signal to devices such as your phone to receive. Each GPS satellite broadcasts a navigational message towards Earth which contains an extremely accurate timestamp, which is obtained through an atomic clock which is on board these satellites. And the satellites also broadcast their position at the time of broadcast, with all GPS signals broadcasting at 1.5752 GHz and 1.2276 GHz. These 2 bits of information allow you to work out your position on Earth. With these satellites all sending exceptionally accurate time down to Earth, your phone or GPS receiver can compare the difference of time between when the signal was sent to when it was received to work out the distance between you and the satellite. By multiplying this time difference with the speed of light, as the signal is sent at the speed of light, you can begin to get the distance away you are from that satellite. As these satellites are also sending whereabouts they are, you can begin to draw spheres around the satellites, with you being somewhere on the outer border of that sphere. As we introduce more GPS satellites into the mix, we begin to get closer to where we are. By calculating the time differences between these satellites, we move from having no idea where we are to being able to pinpoint where we are, typically down to 5 to 10 meters on average, with the potential error being around 15 meters. There are a lot of factors which escalate the potential error, but the most significant is due to the ionosphere, a part of the upper atmosphere extending from 60 kilometers to 2,000 kilometers, where free electrons occur frequently enough to have an appreciable influence on the proportion of electromagnetic waves passing through this layer. This error is substantially smaller when satellites are directly overhead, compared to being larger the closer the satellites are to the horizon relative to you, as the path between you and the GPS satellites goes through more of the atmosphere compared to being directly overhead. Even things such as small variations in the atomic clocks found on board these satellites can cause major errors. A clock error of 1 nanosecond can translate to a 1 foot or 30 centimeter miscalculation. Then the theory of relativity kicks in, with the atomic clocks ticking ever so slightly slower than clocks which are stationary on the ground, which translates into a 7 microsecond a day delay. General relativity then also kicks in, with the effect of the gravitational frequency shift being far greater than the 7 microsecond per day delay due to the velocity relative to Earth. As the theory states that a clock which is closer to a massive object will be slower than a clock further away, the atomic clocks on board the GPSs are faster by about 45.9 microseconds per day. Combining the 7 microsecond a day delay due to the satellite's velocity relative to Earth and the GPSs being further away from Earth, this adds up to a 38 microsecond delay, which if left uncorrected would translate through to a 10 km a day pseudo-range error, rendering GPSs invalid from the get-go if this was not to be taken into consideration. This is compensated by the GPS's clock's frequencies being slightly slowed down from 10.23 MHz to 10.229999999543 MHz to cancel out the effects of relativity. So next time you turn on your GPS on your phone or other device, you should now realize just how much physics and maths is going in towards you finding your own location. Thank you for watching. Be sure to subscribe.
Okay, so don't worry about the maths. The point is, the maths is complicated, but someone's worked it out for us. So that's how GPS works, and yes, yeah, the maths and physics is really complicated, but luckily they've worked it out. And as I said, there is an error in the calculation of your location. And sometimes these can be corrected by these continuously operating reference stations, so to get more accurate readings. Okay, so that's GPS. Any questions about that? Most people would have used GPS at some point or another, almost certainly. Well, yeah, almost definitely everyone would have used it. Okay, so that's sort of primary vector data capture. What about primary raster data capture? Primarily, this is remote sensing data these days. It can be what's called passive or active. I'll explain what that is in a minute. And then then things like resolution become important. And there's 3 types of resolution for sort of remotely sensed imagery. So spatial, spectral, and temporal, and we'll talk briefly about that. Okay. So who knows what the difference between passive and active remote sensing is? No one's going to suggest something? Is anyone going to have a guess? No? Someone must have a guess.
I can't quite remember. I think it's active where you like send a wave out and then like catch. Yeah. So you're like creating the wave or the
Yep.
wave.
Yep. Wave.
You're
Yeah.
sending out
More
short
usually.
and
Yes.
you're
Yep.
receiving the
Right.
response.
Yep.
But with passive, you're just receiving say light.
Yep.
That actually occurs.
Yeah. That's exactly right. So. Yeah.
Radar.
Yeah. Yeah. That's right. So. There's a really good, the camera and radar are good examples of that. So yes, so it's exactly right. So passive is when you're just receiving the thing you're recording is energy from the sun, and active you're actually generating the energy source yourself, like radar. Yeah. So that's exactly right. And actually, I'm going to illustrate this with your eye. Your eye is a remote sensing device, basically, and it receives information or energy from the world, from our surroundings, and interprets that in our brain, and it's sort of what a GIS tries to do with remote sensing. So yes, so passive is basically you can imagine your eye, you're getting solar radiation from the sun, it reflects off objects, we receive that energy in our eye, and then the brain interprets that. And exactly the same way, if this was a detector on a remote sensing device like a satellite, then that would be the same. Active remote sensing is basically where you have a light source. So this is the equivalent is if you're out at night and it's dark and you have a torch and you're shining the torch on things, you're creating your own energy source, reflects off objects, and we still are able to interpret that from that light source. So examples of this are radar, for instance, and there are some active remote sensing approaches such as LiDAR, which we'll talk about. So that's the distinction. So some things to consider about remote sensing, and perhaps some of these relate a little bit to some of the things we talked about yesterday in your prac. You looked at what happens when you change the resolution or the size of your cells on your raster data sets. And the same is true for remote sensing. So if we think about resolution, we mean what's the cell size? The spatial resolution, we're thinking about what the cell size is. So some satellites will record things at 30 meters, some will be down to like 20 centimeters and so on, cell size. And obviously, the smaller the cell size, the more information you have spatially. But there's another aspect to remote sensing, and especially in terms of satellite imagery, is that the temporal resolution is important. So temporal resolution is how often through time you get an image of the Earth's surface at the same place. And so some satellites will return to the same place very frequently, and so you'll have a high temporal resolution. So you might be every day, for instance. Some satellites don't return for several days, maybe 6 months to the same location. So sometimes you're getting very frequent measures of what's on the Earth's surface, sometimes not very frequent. Things like aerial photography tends to be very high spatial resolution, so very small pixels, but are often not done very frequently. So they will, unless someone hires a plane to do the airborne remote sensing, you don't get anything in between, and those tend to be done less frequently. And what you find actually is that if this is a graph of temporal resolution, so this is how often it's recorded, and this is your spatial resolution. So this is the size of the grid cells in a raster data set. And you tend to get, not perfect, but you tend to get a negative relationship. So things that are high spatial resolution tend not to be collected very often, but things that are low spatial resolution tend to be collected more often. Okay? So that's the spatial and temporal resolution. And spectral resolution is basically, so what the sensors actually detect are wavelengths of light. Okay, so this is the reflectance, this is the amount of light in each different wavelength, and these are the wavelengths here. So this is a graph of reflectance of different wavelengths. Okay, so this might be something that, and the way remote sensing actually detects what's on the Earth's surface is looking at this spectral signature. So this might be green vegetation, so you get this spectral signature. It reflects mostly things around this wavelength. This is bare soil, so it looks very different. So it tends to reflect things light of this sort of wavelength. So if you can characterize those spectral signatures of different things on the Earth's surface, you can then work out what's on the Earth's surface. But what satellites or remote or sensors actually do is actually divide these wavelengths into bands. So they'll have a band of wavelengths that they calculate or record reflectance for. And so there'll be bands of wavelengths and you'll get a number for each one at each pixel. Okay, so you don't always get this. You don't tend to get this nice curve. So some satellites or that have very high spatial resolution will have very small bands. They'll have lots of them, so there's lots of information. Whereas if it has a low spectral resolution, it might only have a few bands and has less information. So again, the size of that band is what's known as the spectral resolution. Okay. And so this is just an example. Landsat imagery, or Landsat satellite has 7 bands, and these are the wavelengths. Okay. So it has for each band is a different wavelength, and it has what's known as a panchromatic band, which is a green near-infrared band. And then this is the resolution of those bands. So that has in terms of spectral resolution, it's okay, and a 30-meter resolution and a 16-day repeat cycle. So it's a reasonably, in terms of the scale of the whole surface of the Earth, it's a reasonably high resolution images you get, and it has a reasonably rapid return time. So every 16 days, you're getting an image of the same place on the Earth's surface. Okay. Used a lot for mapping land cover across sort of global and regional scales. So that's an example. So that's passive. So if we think about active, the example I'm going to show here in terms of active remote sensing is called LiDAR. This basically is a very high resolution way of collecting information. So it's based on laser. So it's usually airborne. So you have a sensor on a plane, and it fires a laser out onto the Earth's surface, and then that bounces off the Earth's surface or some objects on the Earth's surface, and then it records the time it takes to get back to the sensor, and then it knows the height of that. So it knows exactly where the plane is. It knows the height, so it can reflect off the surface of buildings, vegetation, and so on, and you can get a very accurate estimate of basically the elevation or surface of the Earth's surface. So it's very high resolution, very high precision and accuracy. Okay. So there's an example of some work we've done with LiDAR, where I'm interested in sea level rise and how it influences coastal ecosystems, and this is an example where we needed a very high resolution digital elevation model, and because when you're trying to simulate the effects of sea level rise in coastal systems, having a very accurate representation of the elevation is really important. If you have a very coarse representation, you just tend to get lots of errors, or it's very inaccurate. So these LiDAR, a digital elevation generated from LiDAR, it's a very accurate representation of the Earth's surface, and combine that with land cover to then estimate changes in distribution of vegetation types across southeast Queensland. And here's an example of this area, and then we were able to sort of map out changes in mangrove systems over time due to sea level rise, and show that a big potential increase in the extent of mangroves over time. So that's an example. Some more recent stuff we've been doing in Brisbane is using LiDAR to actually map vegetation structure. So you can get quite good estimates of vegetation structure, and because you get the laser pulse, you can get several returns from one laser pulse. So it can partially reflect off vegetation, and then pass through and reflect off some other bits of vegetation. So you tend to get multiple returns through, say, forests, and then that allows you to basically calculate density of vegetation. And so we're able to look at the structure of vegetation across Brisbane, and there's some maps there of sort of structural complexity that we've been able to estimate from LiDAR. And we're able to do that at about a 2-meter resolution across Brisbane. This is just an example of another sort of thermal imagery. So this is airborne thermal imagery. So it's really trying to, it's calculating basically surface temperature, and you know, this is these are the degrees of that surface temperature. Okay, and you can link that to land cover. So we're doing some work trying to link surface temperature to land cover and look at how vegetation reduces temperature in cities and so on. So again, I think that data is airborne, so collected for Brisbane. Okay. So and the distinction between that and the Landsat is that that this just records a different wavelength. So it's recording that wavelength associated with temperature. Okay. Remote sensing. I know that we don't really cover much remote sensing in this course, a bit, so it's just really a brief introduction to remote sensing. Okay. Any questions about that? Okay, I'm going to touch quickly on secondary data capture, but I'm not going to spend too much time on it because we don't do much of it. In the prac, you'll sort of do some secondary data capture because you're going to digitize some areas. But you're sort of doing it from a digital image. It's really just an exercise in digitizing and getting information into a GIS. But largely, we don't do a lot of it anymore. But basically, I wanted to mention it. It's really the conversion of data collected for other purposes, so non-digital purposes. So this could be maps, photographs, and so on for use in a GIS. And as I mentioned, less important these days. But certainly, a lot of the data in the early days of GIS came through this process. Okay. So there's various ways that I guess that data can be imported into GIS. One is just what we call digitizing. So this is manual digitizing using a digitizing table. So you don't see these around very often, but you have a table and a map, and then you have this mouse, essentially. It's like a mouse or a cursor that you move over the map to draw outlines of objects and so on. There's manual on-screen digitizing. So this is where you have you've scanned a map, or you've got an aerial photograph, for instance, and then you're just using the mouse to draw outlines of objects to what we call digitizing. And you'll do this today in the prac. And there's another approach called vectorization, which takes a raster image that might be scanned and then tries to generate. So it might be a raster image, this might be a scanned map or aerial photograph, and then has an automated process to try and generate vector polygons and lines and so on from that. And that's another approach. So manual digitizing, I guess there's probably maybe one important point to make is that basically you're just moving a cursor to generate points across an outline of an object if you're making vector data. And there's two ways of digitizing. One is point mode and one is stream mode. In point mode, you're basically saying, you're going to each point and saying create a location there as part of your polygon, and then you go to another point and so on. You choose your points manually, okay, as you digitize. Stream mode is a little bit different in the sense that you set some parameters about how many points you want, the density of points on your shape, and then you just move your cursor across the line that you wanted, where you want to create that location, that object, and then the GIS essentially creates the points for you. Okay? Two different ways, and you'll think a little bit about today about the pros and cons of each one, and when you might, the accuracy of each one. Okay. Secondary data capture as well, scanning maps, aerial photography, and that's a key part of it. Okay. So that's secondary data capture. As I said, we don't do much of it anymore. So you don't need to worry about it too much. And then the last thing I was going to mention was a thing called georeferencing. And we're not going to do, in the practicals, you're not going to do any of this. But basically, when you have a aerial photograph or a remote sense image, it's generally not georeferenced to the surface of the Earth. So by georeferencing, what we mean is taking often this is for raster data sets, but could be for vector, is taking a data set and actually georeferencing that to the surface of the Earth. So actually putting it into a coordinate system. And what you often find is that there's distortions in the, just due to the atmosphere and so on, and the lens that's used for taking an aerial photograph or a satellite image, then, or the sensor, there's distortions in the shape of that image. So it doesn't fit nicely into any particular coordinate system. So what we usually do is we take our image and we create what's known as control points, and then we match them to places of known coordinates. So you might say, well, okay, here we've got an intersection of a road in our image, and we've got another image which says, well, we know where that intersection is, and we basically pair up these points. Okay? And then then the GIS does a transformation of the original image, to force it into the coordinate system you want it to be in. So maybe this illustrates that. So you get your original image, and then you link up these points, and it basically transforms it into the correct coordinate system. And so because it's not going to match perfectly, it does some bending and twisting to do that. Okay? And there's a range of different transformations you can choose. Basically, there's different ways. I mean, there's what's known as an affine. This is just a linear transformation. It basically allows it to shift and scale and rotate. But then these second-order polynomial and third-order polynomial allow it to sort of to bend and twist and so on. It's a bit like if you have I don't know. So you have a plastic sheet, for instance, or a plastic bag, and this will allow you to make it bigger and smaller and twist it, whereas these allow you to sort of bend it and move it around. Okay, so it depends. But these just need more data points to do this. So it depends. This is the simplest transformation, and then these you just need more points and more links. You need more of these links. Okay. So we're not going to do that in this course, but it's important that you're aware that that's a process that whenever data is collected, spatially, especially from remote sensing images and aerial photography, there's a process of georeferencing it that involves this transformation. Most data sets that are collected by commercial companies, they do this for you, so you don't have to do it, because this is really time-consuming, and it's a pain. So I've done it many times sort of manually, and it's painful. But a lot of data sets these days, the commercial companies do this for you, so it actually comes georeferenced. Yeah. Okay. So anyway, important you're aware of that. Okay. So that's it on data capture. The second half of the lecture, we're going to talk about accuracy and errors. So we're going to do another exercise as usual. Now we're going to do this in your groups again, and I've basically given you 3 different maps, and basically I want you to take those maps and basically have a discussion about what type of data are in those maps. So we've got, and I'll give you copies of these. They've got copies in the. I've got some printouts. So there's a map of tracking turtles with GPS. There's a map of forest cover change in Paraguay, and a map of topographical complexity and roughness in a benthic seascape. So just what I want you to do is look at these and discuss with them the type of data that's being used. I want you to identify whether you think it's in situ or remote sensing. Sometimes the answer is not obvious, but I want you to discuss that. Whether it's primary or secondary, and whether it's passive or active, and also what you think if it's remote sensing data, what you think the spatial and temporal and spectral resolution are. And some of them, the information's in there. So it's really just looking at some data, thinking about the type of data it is, and what some of the characteristics are. So let's do that for 10 minutes in your groups. So I'll bring around some of these printouts to the tables. If you want to draw on the boards or whatever, you can do. But let's do that for 10 minutes, and we'll go through them as a class as well. So, okay. You can grab Yeah, my printout's just in black and white, I'm afraid. There you go, I'll give you a couple of those. Yeah, don't know. You're cold or hot? Cold, are you? Everyone's cold, okay. Okay, don't know. I can, probably not, but I can perhaps phone someone and say, it's cold. Yeah, right. Maybe it's because I'm moving around and I don't get cold, yeah. Yeah, all right. I don't know whether I can do anything about it now, but I will ask. Yeah, I'll see if we can make it a bit warmer. Yeah. Did you have one of these? Yeah, there's 2 or 3 there anyway. Okay, so have a discussion. I mean, if you want to just pick one of the maps, that's fine. Just pick one of the maps and work on that. Do that at will. If everyone picks a map, then between us we'll probably have covered all 3, and we can just go through them quickly in class. Okay, let's have a look at these maps then. So the idea of this exercise is just to give you, I guess, some experience in just thinking about data and where it comes from and the characteristics of that data. And I know from the maps it doesn't have all the answers there, but that's okay. I think you can speculate a bit and think about what parameters might determine some of the things like resolution and so on. But let's just go through them as a class anyway, and I guess hopefully if everyone did a map, someone would have thought about each map to some extent. So this tracking turtles, it's what sort of data type is it? Sorry? Vector? Yeah. So if you think I know we had a discussion about whether we're over there about whether we're going to look at the bathymetry data or the vector or the GPS data, but certainly vector data. And is this, I guess, in situ or remote sense? In situ. Yep. So it's sort of like the example of the tracking giraffes or cows was the same thing. Primary or secondary? Yeah. So it's probably primary. I think whether it's passive or active doesn't really apply to the GPS, but if we were thinking about the bathymetry data, do you think that would be passive or active? Passive? Sorry? Active. Yeah, I don't know much about measuring bathymetry, but I'm guessing it's active. It's probably, I know you can use LiDAR to get depth data, and probably sonar, I think, so they're all active. So it's, I don't think, probably it wouldn't be passive anyway. And then is there any consideration of spatial, temporal, and spectral resolution? I guess if you're thinking about GPS, there's nothing, spectral resolution doesn't apply, but what about temporal resolution? What might that refer to in a... Yeah, so how often you take the measurements. So you can, if you're recording data every minute or every few seconds, that's very high temporal resolution. But if you once a day, it's lower temporal resolution. Yep. And I guess spatial resolution probably just applies to, in some ways, to the accuracy of your GPS locations. Okay. All right. So I mean, when you're using things like GPS tracking data or GPS data, these are things to consider. How often are the measurements taken? How accurate are they, and so on. Okay. Good. Right, let's have a quick look at the next one. So this is forest cover change in Paraguay with Landsat imagery. And data type? Sorry? Raster, yep. Is it remote sense or in situ? Remote sense, yep. Primary or secondary? Primary. These are all easy. Passive or active? Passive. And what do you think the spatial and temporal and spectral resolution are? Sorry? Yeah, they all apply. I guess I showed you a slide with all those information on. Actually, it might be in that. Yeah. 8 bands, 16-day return interval, and 30-meter resolution. Yeah. So again, I guess you need to know these things because if you're using it to understand a process that operates at scales below 30 meters, it's probably not going to be very useful. Okay. So, but for mapping forest cover change, 30 meters is reasonably high resolution, spatial resolution. Okay, good. What about the last one? So this is an example, actually, of the LiDAR use of LiDAR to map a seascape. So data type is going to be raster. Yep. Yeah. Yeah. So what you actually do with LiDAR data, you actually get with LiDAR it's a bit in between because you actually get points. So you actually get a point. It's essentially a vector layer of point. You have a point and an exact location, and then data on the heights of the returns. And so often what we do, we turn that into raster. So we'll grid it and have a number of points so we have at a resolution where you get at least a certain number of points per cell, and then use that information directly. But the raw data is actually a set of points. So it's sort of a bit in between. In situ or remote sense? Is it? Is it in situ? This is LiDAR? Remote? Yep, remote? Yep. Bit of both? No, it's definitely remote. Yeah, because your sensor's going to be presumably on the surface somewhere, and you're recording pulses of laser, go down there and they return, and you're recording the time it takes. That's a remote sense. And then the resolution, spatial resolution, 1 meter. Yep, it's a pretty high spatial resolution. Spectral resolution doesn't really apply in this case because you're not getting information on a range of wavelengths or bands. Essentially the information you're getting is elevation or depth. And temporal resolution. It doesn't really say, but I suspect being LiDAR, the sort of temporal resolution is quite low probably, is my guess, but it doesn't say. So it's not like it's well, usually the data collection using LiDAR is often commissioned for certain things. There may be examples where it's a regular thing, but often because it's expensive, the temporal resolution can be quite low.
Would that be relevant at this time?
Yeah, but it might not be relevant. You're right. Actually, it doesn't matter. Once you've got it, you've got it, unless it can. It wouldn't change quickly. Yeah, and that's a really good point, actually. So things that don't change very quickly, maybe you don't need high temporal resolution. So if you've got things that change over centuries, then it doesn't matter. I mean, this will change, but it's a long-term geological process that changes the shape of the Earth's shape at the bottom of the ocean. Okay, yeah. So that's a good point. So thinking about if you're looking at processes that change very rapidly, you're going to need high temporal resolution. But things that don't change very rapidly, you don't. Okay, so yeah, that's good. Okay. All right. The last bit, I'm going to whiz through some stuff on data quality and error. And the question at the end asks you something about errors and data quality. So I hope this will be relevant. So we're going to look at scale, because scale relates to data quality. And by scale here, I mean spatial scale. I'm going to talk about spatial scale particularly. I'm going to talk about measurement error, and then I'm going to mention briefly something about data management. Okay. So if we're thinking about spatial scale, then geographic data consists of extent and resolution. So who knows what extent and resolution are? The two concepts of scale. Does anyone know what resolution is? Sort of, yeah. So it's sort of like quality and how much, but it's represented as it's conceptualized spatially rather than just amounts of things. Yeah, but yeah, you're on the right track. Yeah. Okay, I'll tell you. So extent basically is the size of the study area. So if your study area is St. Lucia, it's probably a relatively small extent, whereas if your study area is the whole globe, then that's a large extent. So the basic extent represents the scale, size of your study area, whereas resolution is the size of your geographic units or your measurement units. So all the stuff we've been talking about, cell size in raster, in raster data, that's resolution. So you might have a large or small extent, but you can then the size at which you're measuring the phenomena is the resolution. So that's the grid cell size. And so in some ways, its extent is like the amount, and resolution is the quality in some ways, because the finer the resolution, the higher the quality. But it's sort of framed specifically within a geographic context. So this is an example, same landscape. coarse scale. Sometimes you might hear resolution, so this is coarse resolution. Sometimes you might hear resolution referred to as grain. In ecological literature, they often use grain, but it more or less means the same thing. But at a fine scale or fine resolution, you get much more detailed information. Okay. So why does scale matter? Well, one reason is because of this problem. Well, the problem is this phenomena called the modifiable areal unit problem, and what it says is that that you get different relationships depending on the resolution at which you measure things, and so this is an example. This is just artificial data, but if we're looking at relationships between two variables, same information but measured at different scales, and if you plot them against each other, the relationship here is quite different. So I guess the typical example that is often quoted for this is a study by Yule and Kendall in the 1950s, and they looked at wheat yields and potato yields, I think, in the UK, and they mapped it out at different scales. So they looked at counties versus farms versus, so they found that actually the relationship between wheat yields and potato yields was really different depending on how the resolution at which you measured it. So I guess so you should always be careful. I think when you measure things at different scales or different resolutions, you get different answers, and you'll always get different answers. So what you want to do is try and match. So as we talked about trying to match the temporal resolution of your data to the process you're interested in, you should also do the same with spatial resolution. So if you're interested in ants moving across someone's backyard, there's no point in measuring the landscape in 30-meter grid cells. It just doesn't match the scale of the process you're interested in. But it might be sufficient if you're looking at broad scale land clearing, for instance. It might be perfectly fine. So it's really thinking about the spatial scale of the information you use should match the process you're interested in. Okay. But yeah, so to make sure you're sort of aware of the modifiable areal unit problem. Okay, so that's relevant because I guess that's when you're thinking about errors, well, not so much errors, but relationships between spatial variables, the scale matters. Okay. But what about measurement error? So we talked about GPS being something where we don't always get an exactly accurate measure. There's some error in that. So that's one type of error. But what are types of error or sources of error that might occur in data capture? Positional accuracy? You're reading from the slides, aren't you? Yes. And the GPS example is what? That's that, right? Positional accuracy, yeah. What else? Someone else is reading from the slides. I shouldn't put them up before the lecture, should I, really? Okay. We'll show them, and I'll ask you to give me an example of each. So, positional accuracy. So this is just what it says, like accuracy in the position of something. So that's your spatial attribute. And got an example of that? When's that relevant? I just mentioned it. GPS? Yep. So the GPS stuff? Yep. Attribute accuracy is whether your attributes of the thing you're representing is accurate. Have you got what's an example of that? Street names? Yep. So it could be, you could have the wrong street name. Yep. Logical consistency is, well, this is basically where something is often topographically incorrect. So this might be that the spatial relationships between two objects just don't make sense. So we talked about topology yesterday. Has someone got an example of where a topological relationship might be broken that doesn't make any logical sense? I mentioned one yesterday.
If like a road doesn't meet up with another one,
Yeah, that's a logical inconsistency. So, and that's the one I mentioned yesterday. So you can get these logical inconsistencies. The other one I mentioned was two property boundaries that share a single boundary, and if they don't in your data set, that's a logical inconsistency. And then completeness just means, well, is your data set complete? Example of that, where that might apply? Yeah. Yep. So where you've got satellite image, you've got a cloud cover, you just haven't got a complete data set. You've got holes in your data where you really need data. Okay. Yep. Good. So positional accuracy is basically, so if you think about maybe we can think about the GIS example. If this is your exact location, and then the red dot is where you record your location. If you each time you get the red dot very close to where your true location is, that's high accuracy. If it tends to be scattered around, that's low accuracy. Okay. So that's what the idea of accuracy is. So I guess there's two components to accuracy, and one aspect that I'll mainly focus on here is just how scattered are your points around that. And if it's random, then and each time you do a recording, you get a point somewhere in here, but it's not. It's random, and on average, your average is close to the center. That's called an unbiased estimate of your location. So each time you go out and do a GPS recording for the location of that tree out there, you'll get a slightly different recording. But if on average your location is the true location, that's an unbiased estimate. And so we've done it where we trying to get a very accurate estimate of a tree location. For instance, we'll often set a data logger to record multiple times your GPS location, then take an average, and it's going to be likely to be a better estimate than a single observation. If the average of your recorded locations is not close to your true location, then that's a biased estimate. So there's this accuracy and bias. Okay, I'm not going to really talk about bias, but you can get bias. There's two types of accuracy. There's a thing called absolute accuracy, which is the accuracy relative to your true location. But we can also think about relative accuracy. So this relative accuracy is related to the accuracy of the location of objects relative to each other. And I was going to ask you a question. Which one do you think is most important? Which one do we care about most, probably? Which one? Relative? Yeah, why relative? It's a guess. I don't know. There's no right or wrong answer here, necessarily. But and what circumstances might relative accuracy be most important? Right. So it might. Yeah, right. Yep. Okay. Yeah. But is there a case when this is more important than that? When we're using GIS for answer questions, when is relative accuracy more important than absolute accuracy, or vice versa? Is there? Yeah, I guess absolute accuracy is really important then. If you just want to know area, your absolute accuracy of your locations that define the polygon, for instance. Yep. Yeah, right. And if you're measuring distance between 2 points, this is really important, isn't it? We don't care about this really. I reckon this is more important usually, because I reckon most of the time we're interested in relationships between objects. And often we don't care where we are on the Earth's surface necessarily. We just care about how things relate to each other. That's not always true. I think maybe the area example is a good one. So I don't know. I don't know whether that's true. That's my hypothesis, that often we care about this. And it's possible that this is poor, but this is we have better relative accuracy. That's possible.
So with that, like if something has poor absolute accuracy and a good relative accuracy, would that mean like say nothing was quite aligned with the coordinate system, but it was all
Yeah, maybe it's bias more than anything. So if you had consistent bias in this and these were biased the same way, as long as they're biased in the same way, your relative accuracy could be fine. Yeah, yeah. So, yeah. Okay. So that's absolute accuracy, and absolute and relative positional accuracy. So what about attribute accuracy? So attribute accuracy is where our attributes are wrong, and a good example of this is from remote sensing, where we might have, and often what we try and do with remote sensing images is we take the image and then we try and convert it into something that's meaningful, like land covers. So we might classify our image into particular land covers, but this is not always right. So often we get it wrong, and there'll be misclassifications. So things that were truly one thing we classify as another, and things that are classified as one thing in the image will be something else. Often we measure that using a confusion or error matrix. I think most people get confused with this, so I think confusion matrix is the right term. This is it describes this in the book, but actually the book's wrong. So just be it describes user. Well, it sort of describes it right, but it mixes up user and producer's accuracy. So I'm going to try and explain it very quickly. But we can go over it again later if people are confused by it. So what you do, you create your map, and you have and basically you create points, locations across this map, and then you record on the map, your classified map, what it's being classified as. So in this case, this is the classification data. This is from your map, and you generate a whole lot of random points, and then you determine which of those points are water, which are bare ground, which are deciduous forest, coniferous forest, and which are urban. Okay, so that might be your classification in your map, and then you go out into the field in that location, or sometimes you can just interpret it from an aerial photograph or a satellite image, and you determine what was actually there. So then you say, was it water? Was it bare ground? Was it deciduous forest? Was it coniferous forest or urban? Okay. So, and you get this matrix, and these are the number of. So, for all the ones that were classified as water, 367 of them were actually water. But 2 of them were actually bare ground, 3 of them were deciduous forest, 12 of them were coniferous forest, and 16 of them. Is that 16? Yeah, 16 of them were urban. So we got some wrong. Okay. So out of 400 sites that we classified as water, we only got 367 of them right. So that's a measure, somewhat a measure of accuracy. So we can calculate a thing called user's accuracy, which is basically saying what proportion of water did we get right. And this is called user's accuracy because it's from the point of view of the user of the map. So we're going to take the map and we're going to say, how accurate are my classifications of water? And you can calculate that by dividing the 367 we got right by how many locations we had, and that's 367 over 400, which is, I can't work out the percentage, but you can calculate it as a percentage. That's called the user's accuracy. And you can do the same for every land cover type, bare ground, deciduous forest, and calculating accuracy. There's another measure of accuracy called producer's accuracy, which is from the point of view of the producer of the map. And with the producer of the map, basically what they want to do is that the things that are really water on the ground, they want their map to reflect that as closely as possible. So for producer's accuracy, you're looking at the other way around, and you say, of all the things that were really water, how many did we classify correctly as water? Okay, so in this case, they were, of all the locations that were really water, there were 382 of them. 367 of them we got right. We classified correctly. And again, you can calculate what's known as producer's accuracy, which is the number we got right over the total number that were actually water. And we can do that for each of our land cover types as well. So there's these 2 measures called producer's and user's accuracy. Okay. I've got a little exercise at the end with another confusion matrix if you want to have a go at this, or we can talk about it later. So the thing they get wrong in the book, I think they get users and producers accuracy the wrong way around. So what they call producer's accuracy in the book, this is the Jensen and Jensen book, is actually user's accuracy. So, so yeah, just be a little bit careful when you're interpreting that. Yep. Okay. Logical consistency are really, as I said, topographic errors. So there might be things like these are called overshoots, things don't join up, boundaries are not shared, and so on. And there's a whole range of sort of logical inconsistencies. And often to identify them, we use topology. So if we have topology defined as adjacency or connectivity and containment, then if those are broken, those rules are broken, and that's a logical inconsistency. Okay. Often used to correct data sets or get rid of errors in data sets. An example is the City of Amsterdam used topology to identify where they had errors in their base data. So they had base data of all the roads and property boundaries, sewers, and so on. And these were, and they knew there were lots of errors in it. And they could have gone through manually and fixed all those errors, but then they used topological relationships to identify logical inconsistencies, and then we're able to do it much quicker by partially automating the process. So you can set topological relationships that say if there's two lines that come within a certain distance of each other, then make an assumption that they should be joined together, and so on. So you can use topological relationships to identify logical inconsistencies and then correct those in data sets. Okay. And completeness, again, is, as we said, is just is really just having complete data sets and making sure that your data is complete. And if it's not, thinking about what you might do about that. So this is just an example of spatial data set of infant mortality rates in Africa at a country level, and as you can see, there's at least one hole in the data. There's a couple of others maybe. So there's holes in that data where you don't have data. So that's important to be aware of when you're using data sets. Is the data complete? And does the data not being complete mean you can't do what you intended to do with it? So, okay. Okay, we're just going to talk about quickly a couple of slides on data management. I'm going to talk a bit more about this later towards the end of the lectures, but I thought I'd just mention it here. So, do people know what metadata is? Yeah, so it's data about data, exactly. So it's basically data about data, and if you are given a data set or you're using a data set that someone else produces, it's really important that you know something about that data. And the key things that should be in metadata are how, when, where, and who collected the data. You should have some information about the scale of the data, what resolution and extent was that data collected in. It should have information about the coordinate system, and then also some information about data quality and accuracy. And I guess these are things that metadata should have as a minimum. Okay, and I think more and more now, it's with government open data policies and so on, data is becoming much more available online, and so when people are publishing data online, then it's really important that this information is available. I think governments are pretty good at doing it, and if you go, for instance, if you look at the Queensland Government Spatial Data Portal, lots of data on there that you might find useful, and it's documented quite well, so they've got quite good controls and so on to make sure that there's metadata on there and the data is described well. But I think with data becoming more available online, those controls are not always there, so you've got to be a little bit careful, but and really look at the metadata of some data sets you get online. This is an example of metadata this is from the Atlas of Living Australia, and so Atlas of Living Australia is or is this TERN? I can't remember. Maybe it's Atlas of Living Australia. No, this is TERN, I think, from Terrestrial Ecosystem Research Network. So showing who the author is, who the owner is, an abstract, and then there's more information about the data and what it consists of. So often you'll see standardized, at least people who run data portals try to have standardized forms which actually tell you about the data. And so, I mean, with sharing of GIS data becoming important, there are pushes to have strict metadata standards. They're standard data formats. So I think if you're sharing data, having standard data formats is important. If everyone's using different data formats, it's not very useful. And then there's issues around legal agreements. So legal issues: who owns the data, who can use it, and then more and more become, as I said, portals for the access and storage of data. So this raises a whole range of issues around data management, and there are some organizations trying to I guess, standardize some of these arrangements. And so this stuff is not strictly about capture of data, but it's important for you to be aware of it, and if you're going to ever share data in the future, being aware of these aspects such as metadata, having standards for sharing, data agreements, and so on, and portals is really, where you make your data accessible is really, really important. I'm going to talk more about that, I think in the last lecture that we have. So we're going to discuss that a little bit. But I just wanted to mention it here for now. Okay. So this is the exercise. If you want to have a go at calculating producers and users accuracy, here's a error matrix. You can have a go at that. So if anyone wants to talk about that, let me know. If there's something that's not quite clear, we can work through this example if you like. So I'm going to leave it there. As I said, the lecture today, it's on digitizing and a little bit of thinking about errors and trying to bring data into a GIS. So we'll have 10 minutes and we'll get started on the prac. Thank you.